Remember that the p-value is the probability of being off in the extremes, the probability of getting your p-hat value or more extreme than that. And of course, this isn't just true for p-hats, this is true for x-bars as well when we hit that particular section. So let's look at the inferential statistics sheet here. So when you look at your p-value pictures, you have the choice of a two-tail test, which means you're concerned about being in the extremes of either tail, left or right. Or you could have a left-tailed test, which means you're worried about being in the left tail, or a right-tailed test, which means you're worried about being in the right tail. And the p-value is the area in those respective tails. Of course, for a two-tailed test, it actually takes them together and sums them for you. All right, now if that's the case, let's look at the example we need to look at. The following shows three shaded Z distributions. The shaded areas represent probabilities. Which of these three sketches cannot represent a p-value? Cannot represent a p-value. Explain. Well, the first one, that's pretty obviously a left-tailed test, right? So there's nothing strange about that one at all. Let's look at letter C, which is right below it. Well, this one's a right-tailed test. It's not a very good one because it's not really talking about the extremes from that left tail. So it's a little bit strange because you have so much of your curve shaded, but nevertheless, it includes the right tail, so it counts as a right-tailed test. But the one that can't be is letter B. So p-values are about, let me type this up, p-values are about being in the extremes. They're not about being in the center. So p-values are about the probabilities. Here, let me type this up. There it is. P-values are about the probabilities of being in the extremes, i.e. the tails. They're not about being in the center. This means that B is no good. Is not a graph of p-values. It's almost actually the opposite of a two-tailed test. The two-tailed test would have the white parts shaded dark, and then that dark part in the middle left alone, left white. Okay, so this one is nothing. Or not a test, let me put it that way. Oop. So letter B is the one that isn't any good. All right, now let's think about this. A statistics instructor gave a fair coin to each of two students. The two students wanted to test whether their coins were fair, quote unquote. So they each flipped their coin many times and recorded the proportion of heads facing up. So they're concerned about the proportion of heads because if it's fair, now let's think about this. This will be your hypotheses. If you have a fair coin, what will be your proportion of heads? Well, since it's a coin, the proportion of heads will be 1 out of 2, which is 0.5. If it's not fair, then the proportion will not be 0.5 or 1 out of 2. So that would be fair, not fair. So you assume the dice are fair unless you can prove it otherwise. And if you like, you could put 0.5 in here instead of a half. It doesn't really make any difference. All right, now the students collected their data and each ran a hypothesis test. The test statistics for student A was 1.91, and the test statistic for student B was negative 2.02. Which of these statistics had the smaller p-value and why? Okay, well, the p-value is the area in that extreme, right, in that tail. And I've drawn these, I've exaggerated just a little bit, but you can see what's happening here. The negative 2.02 is farther from the center at 0. Since it's farther from the center, it's going to have a smaller tail, and that tail is what your p-value is. So the one that's going to have the larger p-value is student B, or smaller p-value. Student B will have the smaller p-value. Now let me type up y. There. Negative 2.02 is farther from the center at mu equals 0 than the 1.91. And that means the area in the tail is going to be the area in the tail. for student B will be smaller than student A. Period. Therefore, the p-value, which is the area in your tail, is smaller for student B. And that's what they were asking about. All right, let's stop right here, and then we'll pick up with the next example in the next video, which is a computer output example. So that'll take us the full 15 minutes on our next video.